Hello everybody and welcome to another bonus lecture for Crash Course Electronics and PCB Design. So if you're watching this bonus video and you're already enrolled in the course, you know what these bonus videos are. Basically, I come up with some random topic about electronics, computer science. It really could be anything, game development, anything really that I just feel like talking about, and then I'll make a bonus video about it. The majority of them are about electronics, of course, since the course is about electronics, but sometimes I pivot off. Now, if you aren't in the course, then maybe you're watching this video on YouTube, something like that, so then make sure you click the link and check out Crash Course Electronics and PCB Design on Udemy. Anyway, so what I was thinking was I wanted to do another PCB design on the fly right in front of everybody and just come up with some idea and just build it. Now there's a lot of companies, SparkFun, Seed Studio, Parallax, um, my company, iConstructs.com, we build breakout boards and we'll put like a chip on there, maybe 2 chips, something simple so you can just play with some particular integrated circuit, right? It might be a sensor, it might be an accelerometer, it might be a relay, whatever. And, you'll go to a company and like SparkFun or Adafruit and buy one of these little breakout boards and then connect it up to maybe an Arduino or a Raspberry Pi or something. Sometimes they'll plug in, for example, it might be a shield that plugs into an Arduino, or maybe it's a, what do they call them, a hat, a Raspberry Pi hat that plugs into the Raspberry Pi, or it might just plug into a solderless breadboard and then you just run wires over to it. But the whole point is there's some chip, some IC that you want to experiment with or use or see how it works, and then you need to somehow to connect wires to it, and you got to solder it onto something. Many of these chips are surface mount, so they're difficult to work with, so you go and find a breakout board. So one of the things as an electrical engineer or an embedded designer that you're going to have to get really good at is building breakout boards. So sure, you can find some things at Adafruit, SparkFun, etc. You might be able to find them on eBay and Banggood also. But the majority of your work as a embedded designer, there's going to be hundreds of ICs, if not thousands, over your career that you're going to need to test, and you're not going to be able to find a breakout board because they're fairly maybe advanced ICs, something like that, or they're just not kind of beginner things that people that would be playing with an Arduino or Raspberry Pi would be interested in. So you have to get good at building breakout boards, and it's a pain in the butt. For example, over here you see me pointing once in a while over to my right, your left, about kind of an area where I have a lot of my prototyping boards, and I've got LCD displays. Let me see if I can grab them without breaking it all. So, for example, let me put it in front of the camera here. So here's something that I had to make just to try out this LCD. So what do we have here? So this is off the shelf. So this is an off the shelf board that allows kind of these edge connectors to be soldered to them. So you got that, and then we've got kind of a solderless breadboard there. But this kind of prototyping, you're going to have to do a lot. All right, so you have to get comfortable with it. And for example, say you want to play with accelerometers. Maybe you have 10 different accelerometers you want to play with, and maybe you can only find 2 of them from some other company like SparkFun or Adafruit, whatever, that have breakouts. You're going to have to build the other 8. So the point is, you got to get good at being able to do this. All right. So what I thought we would do today is, let's see, let's go over to, let's just go to Google off this. All right, and let's do. I was thinking, a lot of people try searching for dinner recipes, funny cat videos. Never searched for that in my life. A lot of people need more GPIO. All right, so when you've got some design, some embedded design, or maybe you're playing with an Arduino or Raspberry Pi, or maybe some small processor like a microchip PIC, and you maybe need some more I/O. So you say to yourself, hey, I'd like to use an I/O expander IC. So that's an IC that you typically communicate over I2C or SPI, and it basically has maybe 4 or 8 or 16 general purpose IOs that you can use from your processor to talk to other devices. So this is a really useful thing. For example, the ESP32, right, the IoT device, is an awesome piece of hardware, but it's got really limited I/O. And of course, the ESP8266 has even got more limited I/O. So these chips are not really made to connect to a lot of peripherals. They have everything built in. So maybe they only have 3 or 4 or 5 or 6 or 10 GPIOs, and before you know it, you've used all those up. So anyway, if we search for GPIO Expander, I just want to make sure you know what we're talking about here. So it comes up with some chips here and comes up with some different things. Let's look at some images. So if we look at some of these images here, you can see, and I can tell right off that, so there's one, Adafruit has a GPIO expander. This looks like something that's more, this is really nice. So this right here, this is very cool. So if you look at this, what's going on here is they have a bunch of terminal blocks, and then GPIO expander, some different kind of connectors here. Maybe that's power. These are GPIOs here. And then that way with terminal blocks, you can screw them in. So that's kind of nice. Here, if we look here, that's nothing. Let's see. Where else is something? Yep, here we go right here. So this is a very common IC, this MCP23 series, so by Microchip, and I use these a lot. And so you can see they've just got this IC here, and then they have GPIO-A and GPIO-B, and then B sub CC, and this is SPI right here, ground, and a couple bypass capacitors, and that's really about it. So that's a breakout right there. All right, and then you can connect this to anything. So this one, I guess, yeah. So this one's I squared C only. So now the this particular IC, the 23 series, comes in a SPI and an I squared C. So if we do use this MCP chip, which we're probably going to, because I like it and I use it in a lot of things, it comes in different packages. So it'll come in these kind of SOIC kind of looking packages. It might come in a TSOP also, and it comes in kind of a QFP or a QFN, more like this kind of package, right? Something that's a square. All right, so this right here is a QFP. So that's what, here's another one here. This looks like it's by SparkFun. Everything SparkFun makes is red, of course. And if you look here, so in this IC, I believe this is an NXP chip, the PCF. Same thing, just some IOs, and then now this, I'm not real happy with this because this doesn't have any bypass capacitors and all that. So one thing is, again, whenever we're going to design something, we're going to do the schematic design, we're going to do the layout, and that's what we're going to do in this video, and we're going to try and do it really fast. But we want to have a good design. We want to think about how it's used. Now think about this. If you've got a GPIO expander, let's go back to this one. And this thing right here looks like it has 2 ports, right? GPIO-A, GPA, and GPB. If I make all these outputs, right, and then if I look at the data sheet and says, well, maybe each one can output 25 milliamps, right? Okay, so if I got 25 milliamps and we've got 16 of those, right? What do we got? We got 25 times 16. That's 400 milliamps, right? That's half an amp of current. So we could sink and source a lot of current from this GPIO. So you need to have bypass capacitors. You need to pay attention to noise and be able to have enough current and all that. So you can look at kind of poor designs. So this right here, this design right here, I'm not happy with because I don't see any bypass capacitors, anything like that. And then if you go over here and you look at the this one here, who made this? Is this? I'm not sure whose symbol that is. But anyway, this one's better because I can see some bypass capacitors. So anyway, we don't want to just put, so whenever you build a breakout board, don't just put the chip on a board. Put the chip on a board, put some filtering on the board, put some, maybe some protection for some of the IOs, protection for the communication, add a little bit to it. Don't just throw the chips on the board. So, because that is really, pointless and oh, this is going to go to Adafruit. Yeah, so if you look at Adafruit right here, their designs are always really good. And it looks like, there's some bypass capacitor here and some resistors maybe for current limiting, something like that, who knows. But anyway, the boards are typically like this. They're 2 rows. And then the spacing between these, a lot of times, go to this view here. The spacing between these are so they'll comfortably fit inside of a solderless breadboard, which of course you know what one of those are. Let me grab one here. So let's see here. Where's the camera? So this right here, if you're an Atari fan, this is a Atari 7800 game controller. 7800. This is an Atari game controller. It's compatible with like 2600, 400, 800, and I was doing something with it. But anyway, there's a solderless breadboard. And then if you look at the spacing, if you look at the spacing in the middle here, from side to side, it's across this main row, it's 0.3 inches. So a lot of times the smallest thing you can make is 0.3 inches, or a lot of times you'll see 0.6 inches. And the 0.6 is usually enough space so you can fit an IC. So that being said, this right here, from here to here, may be about 0.6, and it's definitely not 0.3 inches. It may be 0.6, so it can fit in the solderless breadboard and give you enough room to run some wires. All right, and of course, no matter what, we always want to make sure this distance to here is 0.1 inches, and this distance to here across is always a multiple of 0.1 inches, at least 0.3 inches. All right, so those are some of the kinds of things we're thinking about as we're designing a breakout board for anything, right? So we want to put the chip on there, we want to put some power filtering on there, we want to put some protection on there, we want to make it easy to use. Some people might want to solder it to something, some people might want to put some headers in it. So we'll kind of, we'll leave it like this, and you can put headers in there, and we'll, now also you can see this has got mounting holes on here too. So that's another thing, you put some mounting holes on there, maybe so that this could go into another assembly, maybe a big piece of plastic or something like that, and drill holes and then put it all together, whatever. All right. So anyway, that's the kind of thing that we are going to make. And so let's go ahead and start step one, and which is looking for the part that we're going to use. So we're going to go to DigiKey here, and I'm going to type in GPIO Expander, and I think they call it GPIO or IO Expander. Yeah, IO Expander, 91 items. There's a lot more than 91, but so if you look here, there's a lot of different options here, and you can see there's a few different companies that make these, Semtech, NXP, and then Microchip. We can look here. On Semiconductor, Semtech, Texas Instruments makes a couple of them, Nuvoton, Maxim, Microchip. So I've used more or less all of these different products from all of these different companies, and they all have different features. So some of these GPIO expanders are very complicated. So they might have eight GPIOs, they might have 16. They might have open drain, they might have push-pull outputs, they might have the ability when something changes when it's an input. So these GPIOs can be used as inputs or outputs. So when it's in input mode, if something changes, the chip can actually generate an interrupt to a processor, which is very useful, so that you can go do something or go read that data. All right, so you don't have to constantly pull things. So we like that feature. So we like interrupts. We also like to be able to drive currents, high currents. The other thing we want is we want it to be fast. So now, if we go with I2C, the I2C protocol maxes out at about 400 kilohertz. Sure, there's faster versions of it. You can push it up to a megahertz maybe if you want to, but it's kind of a 100 to 400 kilohertz speed. So let's do some math. All right. So if we're running at 400 kilohertz, right? And now, of course, we have the whole I2C protocol, right? And say that we have some bits that we want to toggle. All right, so we have to write those bits out serially. So we've got 8 bits per byte. So say if we just have an 8-bit GPIO port, and I want to do something with it. All right, and let's say that once we get the processor or the chip into the mode to write, maybe writing only takes 2 transactions. All right, maybe we can just write and then we can write again. So maybe it takes 2 transactions. All right, so we say we've got 400 kilohertz we're running at, and now we're going to have to do 2 transactions, and each one of those transactions is got, we'll just say maybe 10 bits that have to be, shifted out with the AX and the NAX and the data and this and that. So we'll just call it 10. We're going to just be really, really kind of optimistic here. So we'll divide that speed by 20. 2 times 10 is 20. All right, so that's 20 kilohertz. So that means that it takes, at 20 kilohertz, we can make a change. So if we want to toggle a bit, we now divide that by 2, right? Divide that by 2, and we got 10 kilohertz. So maybe we can toggle a bit on these GPIOs at 10 kilohertz. That's not very good. And then, I'm probably being way too optimistic. Maybe we can only do that at half that rate, or 5 kilohertz. So that sucks. We don't like that. So really, whenever I do GPIO expanders, unless I'm stuck with an I2C bus and that's all I have on my processor, I will always use SPI. So you see over here the interface SPI. I like using SPI. So what I'm going to do is I'm going to select SPI, and I don't know why I just did that, but we're going to, so that's really interesting. Let's go back here and let's just click IO expand. There we go, 1600. There we go. So, and again, I talk about this in the course all the time when we're on DigiKey. Be careful we were just on the page, we searched for GPIO Expander, and that took us into a sub-search of interface IO expanders, but we actually were in a search of that with GPIO inside of the title or in some text, so that we only got 91 or whatever it was. Now we've got the full 1600. Okay, so be careful. Always make sure you're searching the whole search space on DigiKey or Mouser or whatever it is that you're buying parts from. All right, these search engines are always funny. Okay, so we're going to build this thing. And first thing, let's select it active, number of GPIOs. All right, I'm going to want, we are going to want 16. I want 16 general ones. I want it in stock. I want it row host compliant. And then we're just going to search for cut tape. Interrupt output, yes. All right, and let's apply filters. There's more filters here. All right, now let's see, what kind of interface do we want? We want SPI. We already talked about that. For only 5 remaining. So that worries me. So there's 112, and then if I put it down to SPI only, all of a sudden we only get 5. I don't believe that. So again, the search engine, sometimes when you put another search parameter, search constraint, it over constrains it and you actually get back way less results. So when I see things change that much, I know there's more than 5 things with SPI in it. So let's just leave that off for now. But what I do want to do is we'll just say push pull. I'd like it open drain and push pull. That would be wonderful, but I doubt I'll be able to find it. And then we can go down here to more filters and we can see the package in this. So I'm not going to constrain on package. Okay, so let's go here, apply filters. Okay, now let's see what you got here. So this is looking pretty good. So let's go ahead and do that. Okay, now, all right. So starting off here, we've got the NXP chips and we've got the microchip chips, diodes incorporated, a few Texas Instrument ones. All right, now the other thing is you'll see is they'll say I2C and SM bus, okay? So, you know, what is SM bus? SM bus is similar to SPI, so we'll say SM bus. And then if we go, actually it's similar to I2C. If we go system management bus, and what it's a bus to communicate kind of with motherboards and different things, but take a look at this. System management bus, or SM bus, is a single-ended 2-wire bus for the purpose of lightweight communications. So anyway, it's derived from I2C. It's very similar to I2C, so more or less you can use them interchangeably. So that's what that is, SM bus, and a lot of times motherboards will have it, so you can talk to the motherboard over this bus and kind of interrogate it when the motherboard is doing whatever it's doing. All right, so that's what these things are. All right, so we really want SPI. So let's go ahead and let's constrain down more to SPI. All right, and again, it says there's only 3 things that have SPI. Now let's back out. And again, we're here. I'm going to sit here, and I'm not going to edit this. We're just going to do this in real time. So if we go here and let's just sort on interface, you can see most are I2C, and then some are I2C with SM bus, and then yeah, it looks like. Yeah, there only are 3 with SPI in this case. So we're going to take one of those because we want this thing to be fast. Because with SPI, we can run this thing at like 20, 25 megahertz, right? So we can run this thing 50 times faster. So going back to our example, we said we could maybe get away with 5 kilohertz. If we speed that up by a factor of 50, what does that give us? That gives us 250 kilohertz. So we could actually, from our processor, do something almost a megahertz, right? And we could definitely do audio effects and all kinds of things like that. So I want that speed. Also, whenever I'm doing anything with GPIO, I don't want to spend a lot of time talking to the chip with I2C. I2C is slow. So if you look at, say, a real-time system, and this is the block of time, right? Every cycle or every processing iteration that I have, if I'm on that I2C bus this much doing stuff, that's a long time. So I want to be on that real quick. So in my total block, I want to, whatever I talk to real quick, and I need to do that with higher frequency protocols like SPI. So we want SPI. End of story. All right, so let's pop SPI in there. Okay. And we only have these 3 things. So you can see we've got kind of these 3 different packages here. They're all from Microchip. And like I said, the microchip stuff I've used a lot and I like it. So these are all push-pull. Now, if you look here, it says that these two have this power on reset. This is what this stands for, POR, power on reset. But I bet this one does also. It's just a lot of times so another thing, when you're looking at data sheets and you're looking at online distributors, remember, don't believe everything you read, right? So a lot of this stuff is, copied and incorrect and all that. So you got to, take it with a grain of salt. So all three of these are basically the SOIC, the SSOP, and the VQFN, all right? ICs. Now, they should, you would think, have all exactly identical everything, and so I bet you this POR should have been here also. So anyway, let's look at cost. So the cheapest one, they're all really the same except for this guy, a little bit more expensive for this QFN. And QFNs are a little bit harder to solder and all that because of the pad and all that. So why don't we take a look at these two, the SOIC and the SSOP. So if you look at it, this is 7.5 millimeters wide. This is 5.3. So this one, I think we're going to go with this one. A little bit smaller, a little bit more manageable. All right, so let's see. Now, of course, the problem is, does the tool have a footprint for it? If it doesn't, then we're going to have to make a footprint, which I'm not going to do. So we're going to find something that the tool, and of course we use Circuit Maker in this course along with Lab Center Proteus. But if you're just watching this video, you could use whatever tool you're using, EagleCAD, KiCad, whatever. It's all the same thing. This video is not about Circuit Maker. It's about design and layout. Okay, so if we look here, the part number is this right here. So let's go over to, I've got Circuit Maker fired up here. So we're going to go to Circuit Maker and we'll go to Libraries, and I'm going to plug this in, this SS version, and oh, it does have it. Okay, cool. So it does have this SS version, so we can use that, all right? So if we want to use this particular IC, we can. So let's go ahead, we're going to use this IC. Okay, so that's the chip that we're going to use. So let's get the data sheet and let's take a look at this and see what we're dealing with here, all right? So, and which one we got to be careful. We're using the S, which stands for SPI 17T. All right, so let's open up the data sheet. Same, and then there's two variants. We're using the S variant, which is here. So this is the variant we're using here. So let's take a look at the pinout. So we've got GPIO A 0 through 7. All right, so that's just general purpose GPIO, and then we've got B through 7. General purpose GPIO. Then we've got V sub DD, we've got ground B sub SS, we've got our SPI interface, which is chip select, clock, a serial in, and serial out. Serial in, of course, would be MOSA, master out serial in from the processor, and serial out here would be MISO, master in serial out from the peripheral or slave chip, right? Then we've got reset. So this is just to reset this thing. So we're going to be thinking about maybe we want to be able to control that remotely from our host also. Then we've got these two interrupt lines. So this is cool. So we're just going to run those out also. And then we've got these three lines right here, these address lines. And what these address lines do is these allow you to use different addresses that the chips will respond to when you communicate to them, right? So with I2C, you actually have an address, right, to communicate to the IC. But with SPI, there is no address. There's just a chip select. You select this chip with chip select, and then it's going to respond. But with these, they allow you to have these other inputs here that give it kind of a global address as far as hardware is concerned. So once you chip select it, then as you're talking to it with the protocol headers have to match in the SPI data this address right here. So that's what that is all about. So you can have multiple chips all responding to the same chip select maybe, and then depending on the address inside the SPI protocol, then you can activate each one of them separately and have them do something. Okay? All right, so you can take a look here at the block diagram. So again, there's our SPI stuff, right? Straightforward. Now, if it's the plain version, the 23017, then it's got this I2C, which we can just throw away. And then so this A2 through A0, so this is going here to this I2C. Now, I was just saying that it also allows it to be used as an address in SPI. I may have been wrong about that. So they may, and we're going to go look at this. So on this S version, this should just be for the SPI version. These pins are either used in a funky way with the SPI, like I told you, or they actually might be unused. So because they're over here and they Yeah, they keep them on both, but we'll actually read about it and find out. So that's, I can't remember. All right, anyway, reset is just reset, and there's our interrupt logic. So when something happens, we can get external interrupts. That's really cool. And then we've just got these GPIOs. And I don't think this data sheet drills down. It might drill down to showing what the GPIO pads look like, but they're usually just two FETs, plus to minus V sub CC to ground, and allows you to short them. Yeah. All right. So, all right. Now, so what you got to do here is you got to read this. All right. So I'm not going to read this. I'm not going to go through this much right now. Right. We're like hardware guys right now. We pretend we don't know anything about software or firmware, and we just want to hook this thing up. Right. So the one thing is operating voltages 1.8 to 5.5, 2.7. All right. So here's these different operating voltage ranges. So now the one thing that we're concerned about is what is the voltage that we can do for the 23S17. Can it tolerate 5 volts? Can we run it at 3.3 volts? Then can it tolerate 5 volt inputs? If we run it at 5 volts, right, is that okay? Can we do 5 volt outputs? But if you look here at this, it seems that any of these ranges will be okay, right? And we can dig down more to see what the situation is as far as, say you've got it at 3.3 volts, can it tolerate a 5 volt input, all right? So you can read about all that and make sure of it. And let's see here. Let's see, look at something interesting. Now reset, now this one, so we say, hey, does this one have this POR, power on reset? And let's see. We're going to keep searching for port here. There we go. The on-chip POR circuit holds the device in reset until VDD has reached a high enough voltage to deactivate the POR circuit. So when the device exits the POR condition, releases reset device operating parameters, i.e. voltage, etc., must be met to ensure proper operation. So it does have, like we said, it has a POR, so it has its own POR. So we can just let that do whatever it does, or you can probably put a 100K pull up on that if you just want to be comfortable that something's pulling it up real weakly, and we're probably going to design that in. Now, let's look at the I2C interface. All right, so if we look at the I2C, which we're not using, all right, then let's see here. Let's see. I want to go to where we talk about protocol here. And yeah, so it does look like, so addressing SPI devices. So the S17 is a slave device. Now, if enabled via iocon.haen, pins A2, A1, and A0 with a read-write bit filling out the shows, okay, so it does have a slave address. So the whole idea is, even though it's an I2C device, it will not respond unless unless over here in SPI, the external hardware matches these 3 bits, all right? So that gives you this kind of flexibility. It's sort of like an I2C device. You don't have to have multiple chip selects. That's what that's all about. Now, with I2C, these definitely are necessary because that builds up its address, right? That builds up the 7-bit address. But in SPI, these things are inside of the protocol, but they're enabled via this iocon.haen. So this is an internal register. So when this thing boots up, what's going to happen is it's going to be in some state so that no matter what these are, you'll be able to talk to it. Then once you enable this, right, then only if it matches what the external A0, A1, and A2 are will the thing respond. So I was right that it was using them, and like I said, it's you got to just read through these things and try and remember what's going on. Okay, so that means we're going to export these out on our breakout as well. Okay, now let's see. And again, this data sheet it's not too long. It's like, how big is this? 42 pages. Yeah. So you got to, I've read this thing before, of course. You just got to read through it all and figure it out. And then if we look at what I want to see here is if there's any, yeah, okay, so yeah, supply voltage 1.8 minimum, 5.5, typical 1, and then there's a little note, and it says parameters characterized but not 100% tested. Anyway, go ahead and run this thing at 3.3 or 5 volts. It'll be fine either way, and I can tell you this, that say you're running it at 3.3, and you want to output and talk to a 5-volt device, it will tolerate the 5-volt inputs and it will drive 5-volt outputs, because a 3.3 to the rail is definitely a 1 as far as CMOS is concerned, so it can be used in either way. And of course, it'll be completely compatible with 3.3 or lower voltages like 2.5 or 1.8 is where it starts getting iffy. Okay, so that's it. That's our chip. All right, so this is what we're going to use. So we're going to keep this right here so we can mess around with this and look at it. All right, so let's go ahead and go create a new project. So I'm here in Circuit Maker. Again, if you don't know how to use Circuit Maker, I use it in the course. You will learn this entire package when you do take the course, if you were to take the course. But for now, whatever you're using, we're just going to create a new project here. So we're just going to say add new project. All right, and we're going to make it public, and then we're going to call this, what is this, GPIO, let's call it Crash Course Electronics, and we'll call it GPIO, and then we'll say Expander. Did I spell that right? GPIO Expander looks good, and this is just a generic GPIO Expander breakout board, and that's it. Good enough. Okay, so let's save that. Okay, and we don't need anything here. It's public concept. Don't need to mess with any of this stuff, and we'll just put, what is this right here? These are the different licenses, and again, reduce the commercial as long as it's parcel. Just license must restrict. We want to put just mix tweak work on a commercial. Yeah, this one right here, I think, is this the basic one that lets you do whatever. Doing this for open source. Okay. All right, good. So now we can go ahead and say open design. All right. And there it is. Okay, so now in the design, there's nothing in it right now. So let's go ahead and let's add. So let's start off and let's add new to project. We need a schematic. All right, now my naming convention is I always name it the exact same here. So I'm going to call this GPIO, and I'm going to call this Expander. And then this is version 001, and then what I do is I have 2 or 3 digits, which is the iteration. So as you're doing design, like I'll do an iteration, another, but it's still the same version. So I kind of do this kind of convention, which works. All right, and then we'll go ahead and we'll add also add new to project. We'll add a PCB. We'll do the same thing. All right, and your tool, whatever you got to do that. Okay, and then up here we've got this blank circuit. Okay, so there's not much in here. One thing is I usually like to make these a little bit bigger. So let's see, where is that? Now, another thing, you know, I use a lot of tools and lots of tools, and you know, I become expert at them and then I forget about them. So between designs of Circuit Maker and Proteus and other Altium tools and this and that and all these different things, I forget how these things work. You know, I am human. So sometimes you'll see me kind of waffling around trying to figure it out, and that's okay. So to change the document size, we go here, and I'm trying to remember if, yeah, that's big. We want it smaller. So we want to make this smaller. So we have enough room, but we don't want this crazy. It's a, you know, fairly simple design. Let's try A2 size. A2, and maybe let's go one more smaller. Little bit too big still, huh? Okay, we'll go to A3. There we go. That's kind of what I want. Okay, now there's nothing in here, so now I'm going to save, and I'm going to go ahead and save this project. And then you got to do this, and then you have to go ahead and commit it. All right, and then it's going to commit it to the cloud, to the Circuit Maker Altium Cloud, Vault, whatever they call it. All right, so we're doing pretty good. We're about a half hour in, so I'm going to try and get this done in a total of an hour. So I'm going to start going even faster now. All right. Okay, so we're all good. This is it. All right, so we got our design right here. Now, another thing, when you know, if you're a designer, electrical engineer, obviously you don't want to start from scratch every single time. So inside of my account, I've got lots of projects from the course, and here's one right here. This is a power supply from another bonus video. It's called the Raptor PSX, And this is a surface mount, a PCB power supply. But why I like it is it's got a lot of parts on it that we're just going to steal and use, so I don't have to go searching through libraries and confirming they exist. All right. So we're going to use some of this stuff on here to just speed things up and copy and paste like resistors, capacitors, whatever, so I don't have to kind of search for parts. All right. So the first thing that I want to do is I want to go down and lay down our IC. So we're going to go place. All right, and we're just going to pop it right here. And let's zoom in so we can see what we're doing. Okay, first thing is I do not trust anyone or anything. So what I want to make sure of right now is that the pinout here is actually correct. Okay, and so a lot of you guys know that I develop gaming hardware, and so I just I finished developing the new Intellivision Amico game consoles controllers, the electrical design for the controllers. So one of the other electrical engineers who's working on the console, there's a couple of them. So as he was doing something, one of the ICs laid down, right, which is a massive not FPGA, but BGA, ball grid array. Apparently, either there was a mistake and maybe it would lay down one pin off, or the footprint was one pin off, but the bottom line was the footprint and what it was supposed to be didn't match, and like you make that kind of mistake, the whole thing is shifted, it won't work. So we are going to look and always make sure, don't assume anybody did anything right. Everyone makes mistakes. This is stuff that's very easy to get wrong. All right, so we're going to go through here and look. All right, so GPIO A looks like it's 21, 22, 23, 24, 25, 26, 27, 28. GPIO A, 21, 22, 23, 24, 25, 26, 27, 28. Good. GPIO B, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, ground is 10. Very important that the ground is in the right place. 10. B sub DD, 9. And remember, I'm using the S version, so I'm paying attention to that also, right? All right, let's see. Interrupt A and B is on 20 and 19 respectively. 20 and 19, that's correct. Reset is on 18, that's correct. My address bus here is 15, 16, 17 incrementally. 15, 16, 17 incrementally, that's correct. My chip select is on 11. Chip select is on 11. Clock is on 12. Clock is on 12. SI is 13. SI is 13. 14 is S out. 14 is S out. And I'm happy. All right, so now I know that that is correct. Okay, so that's correct and good. I still don't know if this footprint is totally accurate though, right? So really what we need to do is we need to kind of, once we do the layout and we pop this thing down and we see this footprint, we're going to go to the mechanical of this chip and we're just going to do a sanity check. We're going to check the pitch between the pins and we're going to check the width between the pins. Just do a sanity check and make sure, because you design the whole thing, you got the wrong footprint, you're going to be pretty mad, all right? So, all right, so what do we need here? All right, what do we need here? Let's go ahead and, so if we look here, and there's a billion ways to do this, right? We've got two GPIOs. We can put them on each side of the board, so we can have a board where on one side is GPIO, one side is GPIO-B. We can do that. Then maybe next to one of them we can have the control bus, right? Or we could put both GPIOs on one side and then the other side the control. You can do anything you want, right? The whole idea is just whatever's convenient and kind of small so you can kind of work with it, right? So we'll mess with that in a second. Right now, let's go ahead and let's start putting some hardware down, okay? All right, so the first thing is let's get power in here. So I'm going to bring power in. Let's clean the power up a little bit. Let's filter it a little bit. So what I'm going to do is I am going to get a couple. This is a GPIO expander. I want this power really clean, right? So this is an 805. So that's an 805. So this design, everything is 805. So I'm going to just copy these right. You know what? As a matter of fact, yeah, I'm going to copy these right here. Now I'm going to copy this whole thing. Copy this whole thing. I'm going to copy this whole thing. All right. So everybody knows, if you take my class, I'm really, really, really into power. I build a lot of power supplies for companies, and so I like my power to be really, really, really clean. All right. So that typically means filters. All right. So right here I've got a ferrite filter. So this is going to get rid of any high frequency noise because I don't want that getting into this chip. This is probably overkill, but I don't care. All right. So then let's move these right here. Okay. And move this right here. Okay, and then where's our power right there? So this is pretty good. Oops. And I'm just going to kind of put this right here. So V sub CCN, that's what we're going to call it. All right, let's put some wires down here, just like that. And then there's our V sub DD, and I'll just put this right here. Looks good. Let's get a ground, copy, paste, and W for wire again. All right, so there we go. So now I've got power, and I'm calling this V sub CCN. These capacitors, let's change these a little bit. So let's think about this. So 0.1, I want that. That right there is for high frequency noise. But I'm going to leave this as a 22 microfarad. I want a big capacitor because remember, you know, someone drives all these IOs. You could drive a ton of current in and out, and it's going to be hard to get that current. Where's that current coming from? Well, it's got to go here. It's got to go back through here. It's got to go back through the wires. It's got to go back through the cable. It's got to go back to the regulator. That's a long, long way. But if we have a capacitor right here, we can source that current, right? And we can mitigate trying to pull that current back from the power supply and having any voltage dips. So we're going to leave that as 22 microfarad. Very important on big GPIO expanders. Don't be afraid to put a big bulk capacitor on here. And this isn't a bulk. It's not like 220 or 1,000 microfarad. But for an IC, it's pretty big. But it's a GPIO block. It's going to drive a lot of current. And I want to be able to drive that current. Okay, so we got that. Let's see here. What else? Is there anything else we need? Okay, so on reset here, what we could do if we want is we're gonna bring this out a little bit here, and then what I can do is since I want to make sure this thing always resets, now even though it always resets with power, right? I want to make sure it doesn't kind of float or do anything weird. So I'm just going to put a weak pull-up on here. Okay, so let's go get a resistor. So we're just going to go get a generic resistor. All right, there's our generic resistor, and I can already tell you that this is 805 size. It should be. All right, I'm just going to put this, matter of fact, I'm going to put this, like this. Sometimes you see this kind of horizontal design. A lot of times I like to put pull-ups up, right? You can do that, or you can put it kind of horizontally to power, kind of depends on, what you want to do. So you kind of decide, and we're going to call this R1. So let's start changing some of these reference designators. Let's make this 100K. Hey, and no one said we have to place this resistor, right? But it's good design. Okay, I'm going to go like that. And then W, again, puts down wires in this tool. All right, and now we need power. So that's going to be V sub CC. And now, if we connect this directly here, right? So here's one thing. So here's V sub CC in. Here's where V sub CC is filtered, right? So we can take V sub CC in and just put it to this pull-up, but that's kind of the noisy power coming in. We kind of want kind of the cleaner power after our little filter here, right? So we might go ahead and put another label here. Not going to hurt us. We can put another little label here. In fact, I can put the label right here, all right? And that'll be the same. And I can put that label right here, and I can call this V sub CC in F, okay? Filtered. So now this is a filtered version of it, and now I can put that up there if I want to, and then I know that this is a little bit cleaner power, right? A little bit cleaner power, all right? Good. Okay, so Control S, always Control S things. So now that's about it. We got our interrupt A, we got our interrupt B, we've got our bus here. Same thing. So on the chip select here, say that you've got this chip connected up, right? But you've just got power. You don't have it to a host, and maybe all these GPIOs are actually connected to some device now that you've built, right? Well, I don't want noise just running around on here and writing registers. Who knows what weird stuff could happen on clock and all that. Maybe it does something. So let's go ahead and make sure that this chip doesn't do anything when it's off, okay? So we're just going to go ahead and I'm just going to pull up chip select also and make sure this thing is not, inadvertently chip selected, okay? Fair enough. Just a little protection, all right? I'm going to put that right there. Good. Okay, now, so now I've got chip select, we got everything here. So let's go ahead and let's put some labels here. Now, old school electrical design, you kind of connect everything with wires, right? And there's nothing wrong with that, but moving things is very difficult. You got to drag all the wires. So kind of new school is you kind of put labels or ports on everything. That way you can just grab a block and move it, and you don't have to connect all the wires. So I'll connect some wires, a few little ones that are localized, but kind of things that are going to connect to other blocks, I'll use net identifiers or ports, that kind of thing. So let's go ahead and get some over here. There should be some lying around. Here we go. Okay, so we got, let's get this green one here. All right, and let's go over here. All right, and I like color coding. You know, I do software obviously also. So everything I do, I like to be color coded. All right, so let's go over here. And this one, so this should be, I want this to be bidirectional. IO type, let's see. I'm just going to say bidirectional. I just want the arrows. Now, I don't really care. I don't go into all that making, you know, ports have the right iconography for input, output, power, this, that. It's just too much, right? It's just too much. That's too anal, right? But I like the two arrows. All right, so what I'm going to call this here is I'm just going to call this GPA 0, all right? And then let's make this smaller, okay? Because it's going to have to hold 2 characters at some point. Cool. All right, now I'm going to take that and copy it. All right, now watch this. Okay, and let's copy that. Do everything in binary. All right, and let's go and over here. This one's going to be GPIO B, right? And let's go change the color right now. So we got kind of this green here. What do you guys think? You want to do red? We'll do red and black, maybe a little lighter. Let's do red. Why not? That's cool. I can still see that. Okay. All right, we'll do red. No, you know what? I don't like that idea. Let's make it blue. Let's make it blue. We'll do red for power. All right, make it blue. Okay, and then the text is a little bit hard to read, so we'll go to text color, and we'll make that white. Good. How we doing on time? Okay. All right. Okay, now we're going to copy this. Okay. All right, now let's go fix these. So GPIO 0 and 1 and 2. And of course, I have no one to tell me I'm doing anything wrong. So I'm doing this in real time always. So sometimes I'm scanning at the same time I'm talking here. So hopefully I'm not making any mistakes. And if I have, you're probably saying, Andre, fix that. It's driving me crazy. But I don't think I have yet. All right, and let's go here to 1. Okay, this will be 2. Okay, this will be 3. This will be 4. This will be 5. This will be 6. And this will be 7, right? Okay, cool. That looks good. Let's go ahead and let's put some wires in here. Put some wires. And again, how you do wires in circuit makers, you press W, it goes into wire mode, and then you can just click with the left mouse button and start and stop each line. All right, and see a little crosshair, put it right there. And we do this. Looking good. All right. My save finger is getting twitchy right now, so I want to save this. So right when I get done here, good. And Control S, save. Okay. Back it out, looking good. All right, what do we need here? Let's call this, so the SPI bus, let's go over here. So the SPI bus, and let's go here, and we're going to call, so I'm going to name this a little bit differently. I like using like actual SPI names for things. So this is SPI chip select. So, and I call anything that's inverted, I put an N on it, right? So that's SPI chip select. All right, now let's put these others, and let's color this also before we go any farther. How about SPI? SPI, I don't know. What does SPI feel purple to you guys today? Purple. My wife likes this color, purple. All right. Is that okay? Yeah, I think so. Should we make it white? Should we make the text white? A little bit easier to see. What do you think? Yeah, that's better. Okay, so let's take that, and we've got these 3 right here. 1, 2, 3. All right, so that's chip select. Now we need clock. SPI S clock. And then what's the next one? This is serial in, so be careful. So this is going to be master out, serial in. All right. And okay, so now we see we need to make these a little bit bigger to fit everything. So I'll just go like that. And I'll go like that. And I will go like that. And like that. Okay, and what's this one? This is MISO. Master in, serial out. So this is master in from this device. Okay, let's go lay down these, fix these wires. Okay. Oops. And I unless I'm doing something really repetitive, I don't do speed up the video, right? I like you to see what I'm doing. Okay, there's not a mistake. I haven't even done all this yet, but that make that R2. And while we're down doing that, let's go make that ferrite bead 1, and let's make this C1, and we'll make this C2. Okay, looking good. Control S. All right, getting happy. All right, and then the last thing we have our two things, address bus and our control bus, I'll call it. So on the address bus, so this is the same thing. So on the address bus, we want to, again, to be able to select this, but maybe I don't want to hook this thing up, right? Again, less wires to your breakout board is always a good thing. So the more things you can kind of put on the breakout, that's what these pull-ups are for. It's less work. I don't have to wire things. So why don't we, again, do something here where we put something to each one of these. We could do pull-ups or pull-downs. We could put it at 0, 0, 0, or we could put it at 1, 1, 1. Let's see. Let's go ahead and of course we could also hard code it on here so that you can control it, but it can be changed where we can put a pull up and a pull down, and then you can either populate either one, right? So that's another option you can do. So maybe you want to have multiple breakout boards, right? So let's not get too fancy here. We're trying to do this fast. We're not trying to build an Iron Man suit. So why don't we just go ahead? Let's just pull these things all up. We'll just pull them all up. And that way the address is just going to be 111, end of story, unless you put something different on it. We'll keep the pull-ups weak, all right? So that's R1, R2, 3, 4, 5, all right? But these are the kind of decisions, that you got to make, and, there's no right and wrong decision. There's just, you just decide what you want to do, and kind of figure it out, all right? And kind of do this. They're all going to the same place, so we don't have to copy the power each time. So, again, the way that I think is, this is kind of the same devices doing the same thing. So I'll hook it up to the same kind of power, even though these are all completely identical, right? Why didn't I connect both of these here? Yeah, I could have, but they're on two different kind of pins. So I kind of keep them separate. Maybe because later I want to put these to different things. But since these are all kind of doing the same thing, I'll just have one node here and I won't have to copy VCC in filtered 3 times. That's all, just personal choice. Keep everything clean. Okay, so now we're going to go here. And okay, so now let's be careful here. Let's do this in the least amount of crossing wires. So there we go, like that. Okay, cool. And now we need three guys for this. So I'm just going to copy this right here. And where are you? You're right there. Okay, let's go here and let's go and make these. I'm feeling. What am I feeling? I'm feeling kind of cyan. No, I'm kind of feeling orange. Yeah, let's do orange. And let's see how that white works. That white now. So that white's a little bit hard to see. So let's go ahead and make it back black, orange and black. Okay, that's cool. All right, I don't want to have to go change those colors twice. So I'm just going to go here, and I'll go like this, like that. Okay, and now this is going to be A0. This is going to be A1, and this is going to be A2. I could make these port labels the same smaller width. They don't need to be as big, but I kind of like the consistency of it rather than a bunch of different sizes. So I'll just leave them like that. Okay, so again, there's a decision for everything. You got to be thinking about everything, right? Okay, those are done. Okay, so we're almost done. So there's our address bus, and now let's go here and let's get our final control bus. All right, and matter of fact, so we don't have to do, because we're going to change the color of this. Let's make this one yellow. All right, we'll make this one yellow. Okay, and we're going to use black. That does look good. Okay, good. All right, we're going to copy that. And there, and there. All right, so here we go. So here's reset. So I'm going to call it reset N. This is interrupt A. I'm just going to call it what it is. This is interrupt B. Now, here's another thing. This chip is configurable so that these interrupts are either active high or active low. They also can be tied together, so you can do a lot with these interrupts. So you can just use one pin that'll get interrupts from both port A and port B. You can, I think you can make it open drain, you can make it push pull, you can do all kinds of cool things. It's got lots of different settings is my point that will help you integrate it into your processor. All right. Okay, so now we're done. Are we done? I think so. Let's go over it again. All right, so GPIO 0, A0 to 7, A0 to 7, GPIO 0 to 7, GPIO B 0 to 7, GPB. All right, that's right. We've got some pull-up. Now remember, we don't have to put these pull-ups, but they're nice to have. So remember when you design, always over-design, because it's a lot easier to not put a resistor or something than to put a blue wire and try and make something that wasn't there. So, I always tend to kind of add things into my designs. All right, we've got our chip select. Go into chip select. We've got our S clock. We've got our MOSA. We've got our serial out, which is MISO. We've got our little address bus. We're going to pull that up just for fun. We've got our reset. Which is inverted here, which the power on system will do this for us, but we're just going to put that weak guy on there. And if something happens, it doesn't seem to work, we'll just not put that resistor. We won't place it. And then we've got our 2 interrupt lines, which are outputs. Okay, good, we're done. So now what do we need? Let me grab this whole thing, kind of put it, maybe I'll put it right here. All right, so now what we need to do is we need to look how many IOs we really need, how many pins we need. So we got 16 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10, and so, and I kind of want all these right next to each other. But again, if they're going to go on a solid spreadboard, they have to go adjacent to each other. We can't stack them because then they would short inside of the pins. So we got to be careful of that. All right, so the first thing is, let's go ahead, let's get some 8-pin headers, all right? Some 8-pin headers. Okay, we're almost done with time here. All right, so this may be an hour-and-a-half video, but that's okay. All right, so let's go back to libraries, and let's see here. 8 position header, and yeah, all right. And let's see, let's do 8 by 1. Let's do header 8 by 1. Oh boy. Let's see. Header header 8 position. Okay, here we go. Yeah, and remember, we can put anything we want into these things, right? So you'll see like the symbol here, right? That symbol in that footprint is actually correct, right? So, and here's another one. And, so the point is what they have up here, we can put anything we want into this. All I care about is we're going to use this footprint just as a generic footprint. So actually, see how this is an actual part, this Molex 35362-850. I don't care. I am not going to use this part. I just want this footprint and this symbol, and then I'm going to change what it is. See, like for example, let's go here and place it. Now the only thing about that is that in the PCB view, you're going to have this thing, which is ugly. But here's another thing we can do too. Let me show you this trick. If you right click and you say place and you say component, so we can see the full 3D model. Check this out. We can go to choose and then get out of favorites. No, let's go to octopart. And then, oh, okay. So you see here, so there's a 3D model and it's kind of showing this thing, right? All right, so that, that's okay. This one's unshrouded. What does this look like? No, that's by 2. That's no good. This one, nope. 2 row, nope, that's no good. Okay, so con-shrouded header. Okay, so let's see here. So if we just type in header 8 position, and then of course we want 0.1 inch or 2.54 millimeter. Let's see what that gives us. Okay, there we go. And then we can say single row. Are you smart enough for that? That's not bad. Okay, let's see. See, that's got that. So remember the 3D model, we kind of want the 3D model to kind of match what we're trying to do here. And again, this is why all this takes so long. Either make it yourself, right? Okay. That's not bad. Let's see. Center line, 0.1. I don't know, that kind of works. Let me see if there's anything else. That's ugly. What's this one look like? Yeah, you know what? I'm just going to use one of these right here. This is fine. Okay. All right. And now I'm not even going to put this this part right here, right? What I'm going to put is I'm just going to put, header 8 position, 0.1 inch, and it's just, it could be male or female. It's just, we just need some holes in the board to represent that. All right, so that's it. Okay, and then what am I going to label this thing? We can label it J, or we can label it H's, whatever you want. So I'm going to call it H1. All right, so there is this one here. Okay, now what I'm going to do is I'm going to flip this. I believe it's, is it X? Yeah. So X flips on the X-axis, Y on the Y-axis. Okay, so now what we're going to go do is we're going to kind of put all the interfaces down here. All right, and then we're going to take this, like this, copy it. So then we kind of have this nice delineation. All right, so here's all our interfaces. So now there's that. There we go. Okay, cool, like that. And let's see. Yeah, that's cool. I'm just thinking about names of things. Always thinking of names of things. All right, we could call that HA if we wanted to, just for kicks. We're going to label it on the PCB, but we can call that HA if we wanted to. But we're kind of using numbers, so we'll kind of stick with that. But again, these are all the decisions that you go through. You know, it's just maddening. You know, you make yourself crazy. All right, we'll call this one H2. Oops. Type in too fast. H2. Where am I? All right, and let's go get port B. And then we have to have a convention here. So we're going from 0 is going to go to pin 1 here. All right. And then when we lay the thing down, will that be on the left? Will that be on the right? Whatever we do it consistently. Okay. Okay. Good. All right. So there's that. Now, another thing I like to do is, because I write software, I like lots of comments everywhere. So we're going to take this comment text here and put it right here, and we're going to say GPIO expansion breakout board until I think of a cool name for it. All right, and then we need some smaller text. So I'll just grab one of these I've already done. Come on, grab that right there. We'll go over here. All right, and then we'll just put this, and we'll put this, and right here I'll just put GPIO Expander IC, whatever, right? And then right here we'll just say user interfaces. Cool. All right. Okay, and maybe move this just a little bit. Oh, that wasn't what I wanted. Maybe like that. All right, and resave it. Okay. Okay, so we're looking good. Let's move this here a little bit. This is the process. Okay, what do we need? Now we need this control bus. Okay, so now these headers, I'm thinking of putting them on, there's 16 pins on one side and then 10 on the other side. So I'm almost thinking about putting both of the GPIOs on one side and then put the control on another side. And then on the control, we could just put two 16s and then, or two 8 pin connectors, and then maybe we just have a bunch of grounds for the other 6. That's a lot of grounds, or they could be for something else. So let's think about this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would have 6 left. What could we do with the 6? All right, let's talk about that a little bit. Okay, let's talk about that a little bit. All right, so when you're running buses from board to board, right? A lot of times, if it's a high-speed bus, it's going to be over cables, and you're going to start to get transmission line effects. Now, if you think about this, we're going to supply power to this thing through V sub CC, right? And through ground is the return path. There's going to be one V sub CC going to it and one little tiny return. So we're going to be sending a lot of current, and we're going to be receiving a lot of current back. So it doesn't hurt us to have more than a couple power lines going in and out, since it is a GPIO expander. So I'm almost inclined, well, I'm not almost, I'm going to, I want to put a couple grounds and a couple power pins. Now also, since typically you're going to run ribbon cable like this, you're going to run ribbon cable for some of these signals, right? a lot of times what you want to do is on the connectors of anything that's really, really high speed, for example, the SPI bus, you want to have grounds between these pins so you don't get noise, all right? That helps a lot. So you want to isolate them. So I'm really thinking I want to create a bus here that's got more pins. So this is good. So you know what we're going to do? We're going to put on one side of the board, we're going to put GPIO A and GPIO B, all right? On the other side of the board, we're going to put the control and power bus, and we're just going to have extra grounds and powers, all right? So let's go ahead and let's copy these. We'll just get them both here, whatever. All right, so there's the user interfaces, and we can, as a matter of fact, let's just do this. So pretend the board is right here. So on the left side of the board from that orientation is going to be the user interfaces. On the right side is going to be our power and everything. Okay, that was about that. That'll be cool. Okay, go here, copy it here. All right, let's make this H2. Let's make this H3. All right, so that's nice and symmetrical. And again, what else am I thinking? Well, if I'm going to manufacture this, right, and if I actually populated this with headers, they're all the exact same header. They're just 1x8 headers. Of course, you could use, if they're right next to each other, we could use 1x16 headers. We could use, 4x1 headers. We could use all kinds of things. We could buy, 32x1 headers and snap them in half. But whatever we do, if we use the same kind of parts as much as possible, then that means we're going to lower the price of it. So we're always thinking about that also. Okay, now, so we got this. That looks good. User interfaces, we'll just kind of put that right there. And let's move this over here a little bit. It's kind of centered. All right, now let's go ahead and all we're going to do is we're just going to copy all this down here. All right. Okay, so now on one bus, this is going to kind of be our SPI bus here. So let's take a look here. So this will kind of be our SPI bus. Now here's chip select. So chip select is not going to be a fast signal, all right? But the clock signal and these signals are going to be fast signals, right? So what I'm almost thinking is what I want to do is stagger these with some grounds here. Let's see. Oops. I'll stagger them with some grounds. Okay. So everything is grounded, and if you just want to ground one of them, you can. They'll all be connected. But this way the cables will have really good grounding on it, okay? So we're going to go like that. Now watch this. So I'm going to put this here. So that's pin 1. That's that pin. That's that. All right, and then we're just going to ground this cable. So if I'm imagining someone's using a cable here, it's going to have a lot of ground on it so that we get really, we get really clean. Let's try this. Let's go like this. Watch this. That's better. Okay. And be careful when you're doing this because you might short something you don't want to short. Okay. So now look, we've got those extra grounds right there. All right. Now, so that's kind of our high-speed bus thing. Now, remember we need power also, right? So this is going to have no power, but it's going to have ground on it. Now let's come over here. All right. And we got 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. All right. So what I'm going to do is I am going to, what am I going to do? I am going to put, yeah, I think I'm just going to put these directly here like this. Oops. All right, none of these are high speed. These are all super low speed signals, so they're not going anywhere, right? And these interrupts, these will happen slow also. All right, so I'm going to go like that. Okay. All right. And now we could put 2 power signals here, but we're not going to do that. We'll just have one power signal. We've got these grounds here to protect that, and we'll put another ground. Okay. So we're going to put a ground here, and we'll put the ground right here. Okay. And so right next to each other will be power and ground. So I'm going to grab one of these. This is the only signal that, we are going to grab from over here. So this is our V sub CC in. Okay. So this will have the same name here. So we're going to turn that. Spacebar rotates things in this tool, FYI. There it is. Okay. So this is V sub CC in. So there's our power. That's going to end up connecting to this, which then gets filtered, which then we call V sub CC input filter or in filtered. That's what we use for all these Phillips and all that to keep everything clean. All right, and then there's our interfaces. Okay, so now let's think about this for a minute here. So we got GPIO A, we got GPIO B on the board. Okay, and they're going in this direction in this picture here. We can put them any way we want on the board. All right. So that's cool. And then we've got our SPI bus here, which I've got a lot of grounds. I'm assuming I'm going to have a piece of flex cable or ribbon cable, and it could go a foot or two, right? So at 10 megahertz, we want to make sure that's nice and clean. So I'm going to go ahead and leave that like that. Now, here's another thing also. We could even, if we wanted to, pull these out a little bit and put some capacitors, at least on clock, we could put a capacitor to ground for noise or a place for a capacitor to ground for noise, so that if we get a really fast signal and there's a noise on it, we can filter some of that noise. Another thing we can do is when the signals are coming in this direction, and leaving this direction, we can put dampening resistors. When they're coming out of here, we can put a dampening resistor. So this MOSA, let's see here, this MISO, we could put a dampening resistor, but I'm going to leave that off for now. I don't want to get too much into that. I've got a video that talks about noise and transmission and stuff, so I don't want to over-design this. We're kind of getting end of our time here, so I kind of want to finish this. Let's see here. Let's go here. Yes, I'm still listening. Okay. I think that's it. All right. So I'm pretty happy with that. That's all we're going to do. We're not going to fill any of this stuff out. So that's our design right there. I'm going to save it. I'm going to go back to projects and I'm going to commit it. Okay. Done. Okay. So now what I'm going to do is this. We are going to compile the project. We're going to compile it. All right. And we see duplicate net names. Duplicate net names. It says H22, H224, and H2. Okay, so something's got duplicated here. What did we do wrong? Oh, right here. H1, H2, H3, H4. Let me show you that. Oh, it's already gone. All right, so let's compile again. And I don't see any errors. That's it. It's good to go. Okay, so now we're good. So now what I'm going to do is I'm just going to save this. And then I'm just going to commit this to the cloud. So if the computer crashes right at this moment, nothing weird happens. What are we doing? All right, so now we've got our PCB here. All right, so there's our PCB. And we're going to resize this and mess with it. But right now, this is just a blank PCB, and there's some tools over here to mess with its shape. But what we got to do is we got to get all these parts into the PCB. So how we do that is here. And again, if you're not using this tool, then this doesn't matter to you. We say update PCB document. And you can do this in a number of different ways. You can right click on this view here and all that. So we say validate changes. And we say execute changes. And we say close. Ta-da. There it is there. All right, so there is our design. That looks good. The only thing I don't like are the size of these reference designators. These are always too big for me. So what I'm going to do here is I'm going to go to this thing called the PCB inspector, and I want to show text only. This is a tricky little device. And okay, so it selected them. Show me the text. Okay, here we go. And I don't want to use stroke font. I want to use true type font. And then see how they all got really small now? That's just better so they're not just massive on the board and hard to deal with. Okay, so now you can see we've got all the nets and everything here. And we can kind of start pulling this thing over and kind of deciding what we want to do. All right, so I'm just going to leave this PCB big right now. All right, so here is, now if we look back at our electrical design, we're going to kind of make the PCB just kind of like this. So we're going to have H1, H2, H3, H4. We're going to literally do it like that. Again, we can always do this better, but we don't have a ton of time here. So I'm going to put this at 10 mils for now and pray that I can align these properly. All right, and I'm going to put them right next to each other so that they perfectly align. Okay, we got to be careful of this. All right, we got to be careful of this because we want them to perfectly align, and that is not. All right, so what I'm going to do is I got to put this back down to 5 mil. All right, and there we go. Okay, so this is going to be H2, put it right here. And then now, here are the pin 1s, and so I'm going to rotate this around actually. I want the pin 1s, we're going to put the pin 1s to the left. You can put them to the left or to the right, you know, either way, either way is valid. A lot of times people put pin 1s to the right and then increment that way, but we're going to put them to the left. There's just, whatever convention you do, just do it consistently, all right? That's it. Okay, now we've got this H2 here. Let's flip that around. I'm just going to put this right here. I got this H1 here. I'm going to put this right here for the now. Okay, looks good. All right, design rules. And now what I'm going to do is I'm going to reset error markers so this doesn't annoy me and drive me crazy. Okay, so that looks good. All right, so we will kind of put this, you know, right here. And later we'll kind of decide if we butt that up, you know, all the way to it like that kind of thing or whatever. All right, and then now we've got H3 and H4. We already said, so now we want them the exact same. So we're going to do H3. Where's H3? Here's H3, and then here's H4. So we're going to put these just like in the schematic picture. Okay, all right, looks good. And then we're going to bring this over here. And now we're trying to figure out how big do we get to make this thing, right? So first, we got to make sure that everything is aligned. So you can see this top line right here. We got to make sure that, and again, let's turn off this design rule checking thing before it drives me insane. Okay, and we got that. Okay, and let's put this up just a little bit. And we're going to check this perfectly in a second here. All right, and then we're going to go to tools, and we're going to go to distance, and I'm going to go from center to center, and I'm looking for, to see how big this is. So this is 12 millimeters, or it's 500 mil. Okay, so we said like 600 mil is another good number. So let's move this a little bit. And okay, all these nets are driving me crazy right now. I'm not a big net person. I don't need to see the nets. When I pick something up, it shows it move. So I'm going to say connections, show all, hide all. Okay, that's how you do that. You go to connections and get rid of it. When I grab it, it'll still show me what it's connected to, but I don't need to see all that spider webbing. It drives me crazy. All right, let's put that right there. Okay, so already I can see this chip is pretty big, right? We're going to have a hard time fitting it in here. So first, let's go ahead and let's move this out a little bit more. Move this out to right about here. Let's check the distance. And what's the distance? That's 615. Okay, so if we bring that back 3 ticks, 1, 2, 3 at 5 mils grid, that'll get us back to 600 mils or 0.6 inches, right? And you can see at the bottom it's 600 mil. Okay, now, so this is in here. So the question is, could we route this, right? All right, I could turn it like this. All right, I could turn it like that. That's an interesting. So we could do that, or we could do it like this. All right, so definitely let's go back, look at now, and here's the whole thing. This is the whole thing about layout. You're trying to figure out where things are also. So if you look here, this is on pin 1 through 8, and then this is 21 through 28. So these are on opposite sides of the chip. Oops. These are on opposite sides of the chip. So so now looking at this, it might be better for us if we were to put the header, like header 1 and header 2 on opposite sides, and then we can go almost straight across. That might be a better thing to do, right? And then we put the control, and we'll split the control bus, all right? So now I'm, changing my mind, right, which I'm allowed to do. Okay, so maybe I'm going to do this, all right? Maybe I do that right there. And then let's move this over here. Let's move this over here. And I'm going to flip this around. Okay. So maybe we do that. And let's flip this guy here. And let's go back and let's see if we're 0.6 apart. Where are we? How far are we from 0.6 apart? And that is 630. Okay, so let's bring this in. Okay, and make sure we're on the same level. Okay, this one needs to come down a couple. Okay, so let's see, do we have the alignment here good? Okay, that's good. And the distance is 590. Oh, good. So 1, 2. And, you know, I know this is tedious, but you got to see how to do this stuff. All right, so that's that. So I think we're gonna stick to that right there. All right, then on H3 and H4, we kind of decide, you know, how many. So okay, so if you see that right there, it looks like the majority of them go to the bottom there. All right, so probably the best bet is to, and then let's see on H4, those go to that bottom right there also. Okay, so what I'm going to do here is I'm going to push this up like this. Then I'm going to put H3 here. All right, because I'll be able to get to those pins fairly easily. And yeah, so that's good. So that's going to go there. And let me move this some more. And I want to show you this whole process, this whole thought process, because this is, you know, people wonder, how do you make all these decisions? And when you watch videos of PCB designers do stuff, I mean, this is a really hard process, and it's a pain, you know, it really is. Okay. And again, these reference designators right now, I don't really care where they are. They're just for reference, so I can see what goes where. And then later, now in this one right here, I can go ahead and flip this. And if I flip this, so again, you're always looking for how do things not cross. So if you look at this, each one of these, so you got to figure out, you know, are things going to get twisted around and inverted, right? So like, let me show you something. All right. So say I put this thing right here, right? Let's get rid of this. This is driving me crazy. Let's get rid of our design rule check. Okay, so say if I put in this orientation right here, let's put this right here. Okay, I'm going to fix this and make it proper in a second. Say I put it right here. Now let's go and try and route. All right, so let's see. Let's route this guy right here. Okay, and this guy right here. Okay, so say if we route this and we go in behind it like this. Okay, now I got this one. Now look at that. That one goes here, but we got to be careful because these guys here, that one's going to go there, 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 that one's going to go there. So we got to be careful about these. That one goes there, that one goes there. See, they keep going that way. So if we were connecting in front of the pins, we would be okay. But since we're connecting behind the pins, what if we rotate this around? Okay, so now watch what happens here. So now let's go here, for example. Now we're going to go behind the pins and connect that. Maybe make this a little bit closer for you guys. All right. And now look what happens. Because I rotate it, right, now things fit better. See that? Cleaner. Okay. Okay, so I want to put that like that. All right, so I'm going to get rid of that, and I'm just going to place this. Okay. Now, let's do the same thing over here. Let's check this. So we go here, all right, and we go like this, and we say, hey, this is going to go here, and then we're going to say this one's going to go, oh, see, we got the same problem. If we were going in front, we would be okay, but we're not going to go in front. We just don't have enough room. We're going to go behind. So that means that, oops, I probably want to rotate this around, okay, and put it like that. Okay, now put H3 there, put H4 there. Okay, let's reset our design rules. Okay, all right, that's looking better. And let's put that there, and put this up here just to keep it clean. All right, so we're literally going to put the chip here, so it's easy. And then now look at this distance here. This is not the same. So I'm going to scoot this over because I want it kind of equidistant. So I have the same amount of routing room. All right. I'm just eyeballing it. Okay. Now we've got our all our resistors and capacitors and stuff. These are actually pretty big. So as you design more and more, so these are 805. So these are a good beginner surface mount size, right? 805s. 603 is a little bit more advanced, right? And then 402 is what I would definitely say is an advanced size, right? They're kind of hard to solder if you have to do it manually and build anything yourself. And then 201 is very advanced. 201s are very hard to solder manually. You'll have a hard time. So I think the sweet spot for most designs, once you get the hang of it, intermediate, advanced level, is kind of 402s. But 805s are pretty darn big. There's just not a lot of room for them. Okay. So now the circuit board is definitely we know that all these passives have got to fit in here someplace, so we're going to fit them in there. So let's go ahead and shrink this down. We'll just put these now. We'll put them right here for now. Watch what happens. So I'm going to go to board shape, and I'm going to say edit board shape. And all I'm going to do is drag it in like this and zoom in a little bit. See exactly what we're dealing with. Okay, that looks good. And then I'm going to drag this one down. And okay, zoom in a little bit. And now, you know what, we might want the board a little bit bigger for something that we might want to put up there, but for now we'll just assume that everything is going to fit in here. And again, you know, so many decisions that you have to make. Okay, so that looks good. All right, and then we know that all of these are going to fit, all of these are going to have to fit, you know, inside here, all right? Okay, so now what I'm going to do now is, so the process of routing is going to probably take me a couple hours, right? And so I'm going to speed that process up. But what I'm going to do now is I'm going to just kind of roughly place some of these things. And normally I would place them near the IC, like near the signals, but we're just going to kind of have to put them here. So what I want to do is, first let's start off with thinking about the power, okay? So the power is going to come in, and if you look here, this looks like this is our power input right here, okay? There's V sub CC in, okay? Now, we know that this ferrite bead in our design connects to these two capacitors, which are very close to need to be close to the power pin of the GPIO block. So I need to put those close to pin 9, period. Okay, they just need to be so that their lead inductance is very small. Keep hitting that button. All right, so C1 and C2 are those two guys. So I'm going to put them kind of right next to each other for now. And good enough. And then what I'm going to do is just grab them and move them by where they need to go. So if you look here, it looks like there's that V sub CC right there. So the closest I'm going to be able to get them is kind of at the bottom here. But the problem is I'm going to be doing a lot of routing here. So I'm going to be routing these signals here. So I could take these signals under, but there's no harm in putting these things up here. All right. So what I'm going to do is I'm going to put them up here for now. All right. And I'm going to kind of split them. I'll put one here and I'll put one here like this. And then what I might do is I might even drag this down a little bit like this. You know, and you're just playing with ideas. You're always playing with ideas. So I can connect this, I can connect this. I'm just thinking how, you know, I want this to be. Do I want to put them on top of each other? Do I put them in this direction like this? All right. It's all about what's going to make it electrically correct and what's going to make it route easily. All right. And yeah, put it right here. So for now, I'm gonna leave it right. I'm gonna leave these things right here. Okay, so there's C2 and there's C1, and I'm gonna put U1 here. All right, so that's where that's gonna go. Now all this other stuff, these resistors are all these pull-ups and whatnot. I'm gonna, unfortunately, these are all. So where are these? They should all be connected to our SPI bus And our address bus, yeah, so this is all spine address. So the good news is we're going to be able to put all these down here. So if we go down here and we look, so there's that guy right there. So, and it's going to be connected to a pull-up. So I'm going to just put it right there for now. R4 is right here. And again, when you're doing routing, you're always thinking about escape, escape plans. How am I getting out? I want to minimize how many vias and how many layers and all that kind of stuff. So you got to be careful. And then these are all connected to this power, right? And we're getting that right there. So that's okay. So that looks good. And then we got R5 here. Where's that? And R5 goes right there. So we'll leave that right there like that. So that's looking good. And then we got R1. This is going to probably be so. All right, and then we can put these all on top of each other, or we can spread them a little bit so that we can get wires through them also. So for now, I'm just going to put them right next to each other since they're kind of going to each one of these signal pins. But I'm thinking about right now what's going through my head is I'm going to have to probably, maybe to run these signals out, I might have to go between them, and it might be easier to spread them out a little bit. For now, I'm just going to leave them like that. Okay? All right, and then here, I'm going to spin that around. All right, and I don't want to get too close over here because I might need to get out this way, but just for now, just kind of put it right there. All right, and now we can see this is not lined up for some reason, so let's see what's going on here. Something's not lined. Yep. Let's move this up. Good, and let's make sure this is all lined up. Okay. So somehow. All right, it could just be the graphic is a bit off. The center should be exactly dead center. See that? You got to be, and again, I didn't make these footprints. You got to be really careful. All right. Okay. So this, we got to move this down. We got to move this down. It's not fitting exactly the way it should. Okay. Or we got to move this up. Okay. This should be here. Okay, that's good. And then now what we need to do is, okay, so now I don't believe that this is 0.1 inches from each other. We got to make sure it's 0.1. Got to be very careful. 2.54. Okay, good. And then this one is, okay, we got to be careful with that. That is 2.66. So this other side, check this out, is too low. So we got to go up one. This has got to go up one. There. Okay. Okay, so now, so you see I made assumptions that these borders, these white borders around these footprints were symmetrical. They're not symmetrical about pin 1 and the last pin. So this is, when it's rotated like this, you got to be careful because it's not going to line up. So now let's go down here. And so the pins I care about. Those need to be exactly at the same place. Otherwise, if you put a header in here, it's not going to fit. All right? Okay. And let's check the last distance here, just last little sanity check. It should be 600 mil. Okay, it is. Okay, let's go ahead and save that. Let's go back to projects. Let's go ahead and commit. Okay, now let's take a look at this in 3D, see what we got. Alrighty. Looks good. So that looks good. Okay, so now what I'm going to start doing is I'm going to start routing this. All right. Now when we're routing, let's go ahead and get a trace down here. For example, say we route this right here. So now what width is this at right now? What is my routing width? And so see, there's all these different widths. So now since we're trying to fit things right now, let's just use, we're going to use 8s. Okay. So we'll say shift and do that again. Oops. Here, okay, and shift W, and we're going to say 8, and put it right here for now. And did that make it an 8? And I'm looking down here, and it's making it a 10. It shouldn't do that. Circuit Maker has some little idiosyncrasies that drive me literally crazy. So Shift W, Control W, is it Tab W? No, you gotta start the trace, and then you're gonna say Shift W. All right. Choose width 8. Darn it. Okay, so what I went and did is inside of the design rules, if you click design rules, you go into routing width. I set it to 6 mils, 8 mils, 40 mils, and so now its preferred width is 1/8, so it's doing what I want to do when we start off. Okay, so I'm going to route a few routes for you, and then I'm going to basically just do this whole thing and speed it up because you know, you don't need to sit here and watch this. Anyway, so let's go ahead and do that. All right, so starting from pin 1. And again, we always look at your schematic to kind of get an idea what you're trying to do. So GPIO B is 1 through 8. Okay, so I know it's 1 through 8, so that's a good place to start. So 1 through 8, here we go. So there's 1, and that's up there. Okay, so now I can go out here and make a turn, or I can just go right here, and I'm just going to do this. And this doesn't need to be pretty yet, but we will make it pretty later. All right, and then come out here, and we're going to have to start making these tight turns. Good. And pin 3. All right. Good. Zoom in here a little bit. That's ugly. Let's fix that. Okay. Go to 4. All right. So this is nice. And, you know, routing, if you're a perfectionist, you got to be really careful with routing. You'll drive yourself crazy routing. And so you gotta say it's okay and not go too nuts routing things. And just kind of good enough is good enough. Now, obviously, there's all kinds of electrical rules and so forth that you have to take heed in. But what I mean is just don't try to make it absolutely perfect because you will literally be here forever. All right. And let's get rid of this design rule. It's driving me crazy. All right. Another thing also, we can press, we can go here and let's get rid of the top silk. So this is coming up. So I double clicked right here for those of you using this tool, and top overlay. Let's get rid of that. Apply. So it's not visible. This makes it a little bit easier to see what we're doing. All right. So we don't have all that white text. Okay, so that looks pretty good. And you know, like I said, I'm going to mess with that some more. Now let's do the other side. Okay, let's do the other side. All right, and we want to do this, you know, kind of symmetrical. You know, one design and the other. So let's see here. So since this is here, I can't come out as far as I'd like to. You know, so what I'm going to do is I'm going to kind of go here first. I'm going to see how far I can get away with this. This tool is very slow. When you connect a route, it seems to me like it takes forever to kind of finish it. So you got to just kind of be patient and let it kind of disconnect. Otherwise, it kind of goes into another mode. Very annoying. All right. And you can see I only have one break in. A lot of times I'll put a couple breaks so I have some more flexibility in moving it around. So you can see I'll like do this kind of thing. Right. I'll do that so I can have a little bit more flexibility. Right now we'll just leave it like this. Like I said, we're gonna mess with this, and oops, we're gonna mess with this and get everything to fit if we have any problems. But right now we're just trying to get the general idea of this, and this is why I say you can't be too much of a perfectionist, or you will be here forever. Okay. Okay, so that actually looks pretty good. All right. And then this side looks pretty good also. Okay. And yeah. All right. Go like this a little bit. All right. So now what I'm going to do is I'm going to just route this thing. And I'm going to speed the camera up a lot so you can see what's going on. I don't know if I'll stop during it, but once I get it done, then I'll talk about my decisions. All right, and that's about it. So let's go ahead and route this. Let's take a look what we just did right here. Yep, we're going to just route this now at super high speed. Okay, so we're just going to route this, and so what I'm going to use obviously is my guide here is we've got the schematic, and I'm just going to kind of go back and forth, even though the PCB tool is always going to show us where the net goes by drawing, in this case, for example, whenever I drag anything, you see a green line, obviously that's the net. We can always see that, but it's kind of good to kind of look at your schematics so you kind of know where you're going also. All right, so now, like I said, I'm going to speed this up so you guys can kind of follow along, but not sit here forever. And then I'll kind of slow down now and then and say something so you can kind of see what I'm thinking. So right now my goal is to all these resistors, all right, that we have here. And if we turn on, let's turn this top overlay on here again so we can kind of take a quick look here. So R1, 3, 4, 5. So these are just all these resistors for the design here. And if we go R1, 3, 4, and 5, and we look here, R1, 3, 4, and 5, and we already have R2. So these are just all pull-ups, and then R3, 4, and 5 are just pull-ups on this address bus, and then this R1 is just the pull-up on the reset. So it's really, really easy. All right, so not much to it, okay? So I'm just going to turn off. Now another thing I can do with this particular tool, we can just go to single layer mode, and that's kind of nice also because then it kind of grays out everything, and you can just kind of work in one layer. All right, so I think I'm going to do that so I can kind of see what I'm doing here. All right, so here we go. Okay, so we're getting here now. We're getting most of these traces. So now, as you're laying down tracks, slowly you'll start to see that you might be cornering yourself, or there might be a problem someplace, or you're going to have a tight fit somewhere. So you kind of, you're kind of always looking for those kind of things. And so right now, what's going through my head is I'm a little concerned about, now of course I'm not really concerned about anything because this is a very simple board and we can route it all, but it, just to make it as clean as possible, I'm just a little concerned about running the power up here. Do I want to run it on the top layer? I'm going to run a wide track for it, and then some of these remaining signals right here, I'm kind of trapped here. So here's another thing: when you're routing on the top layer, you start every time you route a track, of course, you can bisect a space. So this right here bisects this space and this space, and now nothing can go through here unless we use a via or go on the other side of the board on the bottom layer. So you're always keeping that in mind. You don't want to cut the board up too much. All right, and there's always, this board, you could definitely do this all on the top layer. I would bet you $1, but we're trying to use the top layer mostly and then use the bottom layer here and there as we need to. So let's just keep going and see what happens here. Okay, so we're getting there, and I think we're getting to the point where we've got most everything routed. Now we don't have ground routed, but we're going to do grounds with a fill. All right, so we're going to use polygon fills for ground, and that will take care of everything on top and bottom. So right now, I'm starting to get into the cleanup mode here. And now you see the IC only has one ground pin on it, pin 10 I believe, there's only one. We need to make sure that's a really solid ground, so we want to make sure we can get ground on the left side and on the right side here when we do a fill. So what I'm doing right now is I'm anticipating this being tight, and I may not be able to, yeah, that's okay. And so what I'm doing now is I'm kind of pushing this over here, pushing these traces over here to create a little bit of room so this ground can fit inside of here. And let's see here. This may or may not be necessary. We'll see when we try and do the flood fills for the ground planes. All right, so I don't like this little jagged thing over here, but just for now we'll leave it to see what kind of goes on over here. All right, and then I definitely got enough room here for the ground. So then I'm looking here, so this pin, 1, 2, 3, 4, 5, 6, 7, 8, this ground, all these are connected, all right, and this ground right here, we should be good. Now, here's where I might start thinking about making my PCB a little bit bigger to let ground get around. So on the left and the right side, if ground doesn't fill, I'll go ahead and make my PCB just a little bit bigger to help with that. Okay, and I think for the most part, now one other thing, I could move these three things over, these three traces over, three tracks, and then I could put this track behind here to be kind of keep the convention the same rather than hitting it perpendicular here. But it's okay as it is now. All right, let's go up here. We got a little bit of some weirdness going on up here. All right, so what is left? What do we have left that we haven't done here? So let's go on this side. And let's see if there's anything we're missing. So we got this pin, we got this one, this one, this one, we got this one here, this one here. It looks like this one, this pin 18. Let's see where that goes. And all right, so now we're going to have these pins here. We got that one. We have that one. We have that one. And this one we're missing. Yep, this one we're missing. So we got to do this one. Now this one, we're going to have to come in on the blue layer, on the back layer, the bottom layer. So let's give ourselves some room here to do that, kind of facilitate that. And we can scoot this over a little bit if we want. We got a lot of room here, so let's go and try and make this happen. Kind of put that a little bit over there, and kind of stagger that via there. little bit more room. All right, and that's fine. Okay, we'll go back to the blue layer. All right, and then we're just going to pull this over a little bit, pull this over a little bit, and then we might want to just back this away just a little bit. That's fine. You know, and it's as much of a science as it is an art. You're just trying to make everything look good and then also make it electrically correct. All right, so we can come through here with blue, and that should do it. So let's go into this last trace here. So go out here, kind of go in between here. Let's get up here, make this nice. Give myself some room maybe right about there. All right, and there we go. And you know, you can spend a lot of, obviously you can spend an enormous amount of time routing, and I usually do. And this is a big big part of embedded design that's you know, underestimated by embedded engineers. So you know, you can use the auto router, and I don't use it, and you know, a lot of embedded engineers I know do not use it. You can, but it usually does such a horrible job. It's just shameful how bad it is. But sometimes you have to use it. Aside from that, though, you kind of have to do it yourself. So another thing is you can use the auto router and then kind of go in and fix it. But sometimes it takes so long to make it, to fix all the just horrible routing that it does. Now, a lot of times the auto router will, you know, it's routing correctly. It's getting timing closure, meaning all the timings are correct and all that. But it's just so bad. You can just see it's horrible. But you can use the auto router, then go back and kind of fix things. All right. Anyway, so I think we're getting there. Let's see. Okay. So I think we've got the majority of everything connected up. Okay, so what I'm going to do now is I'm going to fatten up these power lines. Okay, so we've got this V sub C in here. Oops. So we're going to run power through here. So let's go ahead and let's just make that 25. And anything that I'm going to power. So for example, this pin 2 here, this is like a pull-up resistor. So anything that I'm kind of pulling up and doing all that with power, I'll usually use a 12 or a 15 mil thick. But the actual power that's getting routed, so this is going through this ferrite bead. This is the power line, and here's a pull-up right here. All right, so I'm going to go ahead and make this whatever we made that, which I think is 25. So let's go to the PCB inspector. Let's go here, display all objects, and matter of fact, we'll do tracks. All right, and that's 8 mil, and I think it's 25 mil is what I made this one. Yep. All right, so we're going to make that 25 mil, and then we'll go through here and make all these 25 mil. And again, you know, bigger is better, as big as you can make it, but we don't want to make it so big we can't route other things around it. Okay. Okay, so here is, this is kind of our power rail, and then these are all these kind of pull-up resistors right here. So there's no harm right here in making these thicker, so I'll go ahead and make these all 12s, these pull-ups. All right. And that looks good. Okay, so then here's where we're going to route our power. So as a matter, now I can do it on either layer. Now if you look here, this is all these blues, these blue tracks on the bottom layer kind of covering this top red track. So we're going to have a hard time getting out of here. Now we could potentially put a via here someplace, and then we could come out blue. We could go on the blue layer and go right above it, and then go right up here. So we could do that, and we could stay off this red layer, right? So that's probably what we're going to do. All right, make that clean. So what I'm going to do is right after this ferrite bead, so right here, I'm going to go ahead and go into the blue layer. So we're going to go here, and we're just going to pop a via through there. Now that via is too small, we'll deal with it later. We'll fix it. And then here's our big power line, and then we're just going to bring this directly up into here. All right, and then we're going to pop a via again and go there. Good. All right, and let's fatten that one up, make that 25. All right, now, so our via here, Let's make this bigger, and if I can get it to open up, here we go. So we're going to make the whole size, I'll make that 15, and we'll make the diameter of this 30, so it's larger than larger than the track. And there's rules for via sizes and how big the hole is relative to the plating and so forth. And the bottom line is we just want to make sure we have enough metal so that we can conduct the signal here. And there's also some things about the aspect, the hole size, so the total size, so the holes can't be too big, so that the plating is too small or too thin. All right, the annular ring. All right, so then that's that. So that looks good. Okay, let's take a look at our layer here. So that looks good. And then let's go ahead. These are tight, so I want to get good flood filling here. So I'm just going to push this over here a little bit, and then might as well just drag this out here. Drag, drag, drag. Okay. All right, let's take a look at that. Okay, so that looks good. Pretty happy with the blue layer. The blue layer doesn't look too atrocious. All right, let's go look at the red layer. The red layer doesn't look too bad other than this area here, which we're gonna address that. If we can straighten that back out, I will. Over here, let's pull this down a little bit. These are a little bit tight for my taste. Okay. That's good. And we could probably pull these over here too, but I don't think we're going to. All right, so it looks like we have every one of the signals connected. All right, so now what we're going to do is we're going to actually go run. The design rules. So I haven't set the design rules up, so if I have to change them from default, I will. But obviously, we've got to set the design rules up properly. They're just kind of in default right now. Usually they're sort of okay, but let's see what happens. Right now we're just looking for nets and so forth. All right. So as a matter of fact, let's take a look here. So so we got no errors, we just have rule violation. So if we look here, silk primitive without silk layer, don't care. That's just some of our labels going off the PCB. Minimum solder mask gap, don't care. And then clearance constraint, don't care, and then unrouted net, that we do care, all right? And those are going to be those grounds. So that looks good. So let's go ahead and let's do our flood fills. Okay, so next, as a matter of fact, let's go here, and while we're at this, let's go ahead and turn the top silk layer on so we can see everything. Now let's just start moving the stuff around a little bit. So put that right there. All right, we've got C1 and C2. We could put, why don't we put C1 right there? I guess we could put it right there, huh? And here's another thing, make stuff neat so you can see things, and so that you can put your board together, right? You always want to be able to put the board together easily, and because you're going to be prototyping the first one, kind of. So have some method to your madness of how you place things. And I like kind of imagining lines everywhere and just make everything really neat. And that's what I'm doing here. Now, of course, if I had hundreds of parts, I would speed this up, but you can see this process. This is semi-useful. All right, that looks good. And then, you could put it there, you could put it there, but it's kind of confusing. So instead, we'll just put that one right on top. All right, and then FB1, we could put it right here. So now, as a matter of fact, I'm going to put this right here, and I might want to put some text here describing something, not sure. Now, another thing is we can label all of these pins right next to them too. That's another thing that we can do. All right. All right, so now let's take a look. So that's looking good. Let's look at it in 3D, and now we can really see all the silk. Oh, there's that H4 and H3. Let's go fix that. All right, and all these different views kind of help you see what you're doing a little bit, right? So that's why I go into 2D, I go into 3D. Different views can kind of help. All right, that looks good. Let's go back. Okay, nothing weird. Looks good. Go back to 2D. Let me save that. Okay, I'm happy with that. All right, so now we're going to do a polygon pour. And all right, so let's see. We're going to do top layer, and I'm going to call it top layer ground. It's on the top layer. The ground it's going to connect to, the net it's going to connect to is ground. Pour over same net polygons. Pour over all same net objects. Remove, there's some different settings here. Remove necks that are smaller than 5 mil, that's fine. And where's the dead copper? Dead copper, we got that, is poured. Okay, so all these, and you got to read and figure this out for your particular tool, how this works. But anyway, that should get us started. And I'm just going to kind of do this over the whole surface here, going like this. And this is going to kind of fix everything up and get those few unrouted nets, get all our grounds, and right click. Looks good. And you can see right here, let's go to single, so you can see we've got our ground, we got our ground, we got our ground, ground, ground. Everything's grounded, and then there should be the end. We got that good ground in there that we wanted. Now, remember we talked about this right here. Let's see if I can, if I were to back this out, repour. I am not too happy with that. I'd rather keep it. So I'm gonna keep it like, yeah, I'm gonna keep it with this little funkiness over here. All right, so we've got a good ground. Now, I want this piece of the ground fill to connect here, so I'm just gonna do that and pray. All right, and it's working, so I'm gonna do it some more. Good. We always want all this stuff to be as thick as possible. Okay, now this is a power line, right? This is our power coming in. So let's make this as thick as we can for the pad. So it's 8 mil. So I suspect we can probably get away with 15 mil. All right, and let's see. Yep, good. All right, close that. Okay, so that looks good. Okay, happy with that. All right, so this we've got now, we want to make sure we've got no isolations here. All right, so this all looks good. And nice ground fill everywhere. Ground is getting around all of the pins. That's good. That's good. Okay, so that's good. Good enough. All right. And okay. All right. Let's save that. Now let's go do the ground on the bottom. So we'll do another polygon pour. All right, and we're going to do bottom layer. And the name is going to be bottom layer. And we're going to call it, oops, ground. And the net, of course, is going to be ground. We're going to do over all same net objects. Remove dead copper. I don't know if I didn't tick that on the previous one. We'll have to go back. All right, so here we go. I'm just going to go like this. Very simple. And presto, right click. All right, let's take a look at what we got. We got our grounds there. Ground, ground, ground. All right. And then, you know, this one's pretty simple because there's not much to it. So let's go ahead and see if we want to widen anything up or do anything. All right, so I wouldn't mind some of this filling up a little bit better. So, you know, I'm going to pull this over just for fun and see if I can get a little bit more grounding in here. All right. And let's see here. So if we pull this way down, and you know, I'll sit here and do this and play with the ground fill and try and get as much to fill as possible. All right, now I'm going to force it to rebuild poured. All right, so we got that. All right, so now there is a constraint that's not letting it kind of fill in between here. The spacing, I think it's probably set at 10 mils, so it's not letting things ground fill unless it's really wide. I'm not going to go mess with the settings in this case, I don't think. I'm just going to kind of leave it, and I think I'm just going to kind of do this. Let me see if I can get it to open. You know, and again, this is the process. It's a pain in the butt. You got to do it though. You just kind of play with things, and you can go change your design rules. And let's see if we can get it to do it. There we go. So at least we got that. All right, and then you can see we got this kind of chunk here, and so now I'd like this to be kind of filled here. So, you know, maybe I'm going to, okay, I grab the whole plane. Yeah, the picking is never good. I've never seen a CAD tool that picking worked. It just does not work. All right, let's go like that. and we'll go like that. Just create some symmetry. I like symmetry, you know. I like everything to kind of be and look symmetrical also, and as well as being functional. All right. So you see me kind of play with this. Now, you know, I could do this for a long, long time, and we don't have too much time, so I'm going to kind of stop, I think, it here. But anyway, you can see kind of what I'm doing here. I'm just trying to get as much flood filling, the ground filling as possible, so this thing looks nice. Okay, let's go to 3D. So this looks good, and then let's flip it over. That looks good. Okay, no big complaints or anything. You know, we're not building parts for the space shuttle or anything, so we're just building a little breakout board. All right, so that looks good. Okay, and let's go ahead and let me go back to, go back to the top layer here. Okay, so is there anything big? We've got our power here, there's our power, so we've got our thick power lines. All right, and we got our bypass capacitors there, decoupling. We've got our power going there. Our power is going into our IC, and then our power is coming in on this single pin. We've got a bunch of grounds everywhere. So that is more or less the design. Now, the last thing that we can do is, and I'm going to see if I can even do it. If I can, I'll speed the camera back up, if it's even worth my time to kind of mess with it. All right, is we can start labeling these things, right? So if we go here, all right, we go to say H1. So from pin 1 to 8 is GPA 0 through GPA 7, pin 1 through 8. All right, so if we go to H1, let's go to H1 here. So here's H1. If we look here, here's pin 1. So this is, where's pin 1? This is a GPA 0. All right, so this, the way that we did this, you know, here's 0 through 8, and then on the other side it's the same thing, 0 through 8. So let's see if we can put some text in there and how bad or how good that looks. All right, so we can, we're going to go over here and grab text in this particular tool. Let's get the top overlay wherever it's hiding. Everything is always hiding when you're doing this in real time. Okay, and stop. All right, and let's go here. Okay, so we want true type font, and let's just punch this down to 40 mil. And Arial is really, really, really ugly. So use whatever you want for your font, but I kind of like Metro style. It kind of looks high tech, but not so high tech that it looks ridiculous. I use it a lot in a lot of my designs. Did I just pass it? ME. There it is. Yeah, this one. It's Metro style or Metro style inverted. All right, so this is GPA 0. Now, I don't think I'm going to be able to spell this out. So I'll start off with GPA, and then I'll probably just come down to A0 or maybe GP, or we'll see. But let's just see how big this looks. GPA 0. Okay, so there it is right there. And if I were to rotate it, okay, so it's too fine. So let's go to bold. Next, it's a little too small, so let's go 50. And definitely I want it to be big so I can read it. So we're just going to put A0 there. So let's give that a try. All right, that actually looks pretty good. So let's see. I'm going to go and copy that, and I'm going to replicate it. Yeah. So I think we can get away with this. What do you guys think? All right, let's do this. Won't be too bad. Obviously, we got to move that reference designator out of our way. This H1. So we'll deal with that in a minute. And we'll put another one of these here. All right, so that looks good. Okay, let's go ahead and go in single layer mode so we can see what we're doing a little bit better. All right, so that's A0, A1, A2, A3, A4, and I'll speed the camera up again in a little bit. A6, I just want you to kind of see what I'm going to do here. A7. Okay, so that looks good. And then what I'm going to do now is I'm going to take these and I'm going to copy them over here. And now I need to reflect them. So I need to flip them on X and then flip on Y. And then I'm trying to remember. Let's turn this back. Yeah, so that's good. That's exactly what we want. And let's move this here. Okay, and then let's move these all here, like this. Okay, all right. So let me kind of work on this a minute, and we'll get back in a second. Okay, so I've kind of got that done. So let's take a look. So that looks pretty good. I think we can use those so we can see what we're doing. All right, and let's make sure. So pin 1 is B0 and pin 1 is A0, so that's correct. All right, so what do we have left here? We have our other labels for our SPI and our address stuff. All right, so let's go ahead and, what are we going to do with this? I think what we're going to do is we're not going to worry about it too much, and I'm just going to put H2 there, and I'm going to put H1 here, and as a matter of fact, I'm going to even worry about this less. I'm going to make this 40. All right, and I'm going to turn it like this. And again, we could remove these also, right? We could remove these reference designators, but then it's going to be hard to figure out what we're doing. So I'm just going to, kind of put them right on top of that. And just to be consistent here, I'll do the same. Oops, I'll do the same thing here. And we'll just make that 40. And then we will rotate that around, kind of in anticipation of putting the rest of the signal names. All right. Okay, that looks good. All right. Okay. Okay, so then now what do we have left? We look over here. So we've got all the SPI stuff, the address stuff, reset, and interrupts, all right? So why don't I go kind of and do that, and I'll speed up the camera again. Okay, so I think I've got everything kind of where I want it. So we've got the GPIO ports labeled here. And again, you can kind of strike out a rectangle or something, a selection rectangle or rubber band, and kind of see if everything is kind of on the same line. So I'm just seeing if it's on the same kind of baseline. This stuff doesn't have to be perfect, right? Unless it has to be perfect. So again, you can spend a lot of time just messing around with things, and you got to watch that, because you can sit here just forever kind of tweaking it and so forth. You want it to be nice, but again, you got to get things done. So that's always going through my mind, trying to get stuff done. Now, all right, one thing here that I decided to do was these are the address lines. And you can see I put A2, A1, A0, kind of lowercase. Maybe we could put, because they're in the design, they're called A0, A1, A2. Yeah, you know what? I think we're just going to leave them like that, but in lowercase to differentiate them from these actual GPIO pins. Okay, so that's just the address bus stuff for the setting the address. All right, so that looks good to me. So let's go here. Let's take a look. So this looks correct. All right. Looks good, and I think we could use that. Okay. And now let's go ahead and think of a name or whatever we're going to put to name this thing here. Oops. And now we can put it on the back. We've got the whole back available. All right. So what is this thing? This is a GPIO Expander. All right. So we can call it something like, let's take some of this text here and go here, and we can call this GP Expander, the GP Expand, GP Exp. All right, and we can put this up to 60, and we can call this, 1.0. Let's see what that looks like. GP Exp 1.0. All right, and that almost fits. So I'll just kind of push this down a little bit, push it right here, push this down a little bit, right there, and maybe put it up. Now put it right at the bottom, just like that. Okay, so GP Expand 1.0. All right, and I think that's it. So let's go ahead and save that. All right, we're almost at an hour here, roughly, depending on the editing that I do. So this is a big video. All right, and so this is, I'll probably end up making this 2 parts, actually, because it's taken a long time. We'll see. All right. Okay, so let's go ahead and run our design rule check again. And I'm getting a lot of silk screen issues. Rule violation 60. Okay, 24 silk screen. Minimum solder mask. Clearance constraint, don't care. Unrounded net, that's all I care about. 0. Everything else is just visual. All right, cosmetic. All right, so that worked. So that's good. So this thing is all good to go. So let's go back to projects. So now what we're going to do is we're going to make sure each one of these, I'm going to save that. We're going to compile. We're going to save. I'm going to commit. Yes, I want you to save it and do it all again. Okay, looks good. And let's go ahead and run this, reset markers, run this again. Always recompile, resave, try, do 2-3 times, make sure everything's good. All right, 60. And where's our unrounded nets? That's it. We have no errors. Where are errors? No errors. Okay. Okay. So I'm happy with that. Okay. So now the next thing that we're going to do is we're going to generate the Gerber files for it. Okay, so we're going to generate the Gerber files, and so we're going to go here in this particular tool. Now, again, if you're taking the class, when you do section 8 on PCB design, we're going to do countless examples of designing circuit boards and generating files and all that. So I'm not going to give you a whole course on this right now. I'm just going to kind of do it. All right, and we're going to go to Tools, and we are going to go to Outputs here, and where are we here? We want, let's see, generate outputs. All right, we've got to save the project even though we just saved it. All right, get that ready, committing it to the cloud, cloud this, cloud that. All right, so here is the setup for this. All right, so I don't care about the bill of materials, I don't care about schematics. All I care about are Gerber files. All right. That's it, and the NC, the numerically controlled drill files, I want that. Okay, let's go to configure, and again, I want to make sure all this is correct. If you're taking the class, you will learn exactly how they're supposed to be. They are correct, so we're going to leave those. Now we're going to go to configure the Gerber files. All right, this is correct. Now in layers, what do we want? Okay, so we want the top overlay, we're just going to get them all. We want the top paste, we want the top solder, we want the top layer, we want the bottom layer, we want the bottom solder, we want the bottom paste, we want the bottom overlay. And then there's a layer called outline. We need this outline layer, all right? And the fabs will need a layer that's the outline of the board. So we're gonna have to go and deal with this in a minute. And there's different ways of doing it, but for now we're just going to do this. And we're going to deal with this outline in a second, but let's just see what we get generated right here. Let's go generate. All right, now let me do it again. All right, so we'll say generate. Okay, good. Okay, so now we've got it over here, and it's going to put it in this big long directory, which is the crash course source files. All right, and we're just going to overwrite this. Yes. All right, and then we'll say close. All right, and then let's get back here. All right, we're going to go into this manufacturing directory, and then we're going to unzip this. All right, and we're just going to unzip it right there. Okay, now what I want to do, so there are the Gerber files. Okay, And again, I go over this ad nauseum, and there's the NC drill file. Okay. Now what I want to do is I want to see it. I want to see what is in here and make sure that it's okay. All right. And sorry, I'm putting things on other screens. All right. So basically, we're going to go in here, and let's move this off the screen. Now, one of the tools that I teach you to use in the class is a Gerber viewer and editor called ViewMate from Pentalogic. And let's see, I can't remember which one is working right, but let's try just plain ViewMate. I think this is the free one, and it always wants me to upgrade it. And this is so annoying. Please stop that. Okay, so now I'm going to go into the Gerber files. So here's the Gerber file. So here is, let's see, top layer, TL. There it is. All right, so there's a top layer. All right, so that looks good to me. And always do your sanity check. All right, there is the bottom layer. Okay, looks good. Yep. All right, here is the bottom overlay. There is none. There is no bottom overlay. So we're kind of, it's free these days. You might as well do it. But we just didn't have time. There's the top overlay. Looks good. Nothing looks crazy. All right, and top paste. Looks good. Whoa, looks good. Thanks, Windows, for not doing what I told you to do. All right, there's that. And, okay, there we go. All right, hold on a second here. All right, what else? Let's see. Bottom paste. There shouldn't be any bottom paste because there's no surface mount on the bottom. Okay, that's correct. And let's see. Bottom layer, bottom overlay, bottom solder mask. Yep. So there's a solder mask. That looks correct. And then top solder mask is that one. Okay, that looks correct. And so you see what I'm doing. I'm just going through all these. You need to do this. And then there's some extra little files here. Just ignore them. All right. And now let's go to the NC drill. And it's just this text file right there. There's the drill files. Looks good. Okay. Now we're missing that outline. And again, this is a big deal. You have to kind of get this outline. And let me show you how, even though this is in the class, I'm going to just quickly show you how to do this. So in this view right here, what we're going to do, and depending on the company, so right now I can't see the outline layer, so we have to go over here, and in this particular tool I have to turn it on so I can see it. So these are all enabled here, but if you look, I'm looking for various mechanical layers that are not showing up here. All right, and let's see here. Yeah, there it is there. See that outline layer? And show, it's kind of this, that is horrible. Let's make it so I can see the thing. I always like this color. All right, there we go. So there's the outline layer right there, all right? So it says that it's showing it. Okay, so why don't I see it? I am blind. There it is. There's the outline layer. So now let's go into single layer mode. And if I hit outline, there is no outline. All right, so now we're going to create this outline. So how you do this is, again, in your tool will be completely different, but if you're taking this class, this is what we use. So define, board shape, define from selected objects. Let's see, redefine board shape, create primitives. Yeah, create primitives from board shape. That's the one we want. All right, 1 mil layer. I'm going to stuff it into outline and route tool outline. Okay, and it did it. So now if we go into single layer, there is the outline. So now we have the outline. Okay, good. All right, so I'm going to go ahead and save this whole thing again. And then I'm going to go ahead and do this commit thing. And we're going to go delete the files again over in that directory that it generated them. Okay, so here we go. What are we doing? We are doing these outputs. So we're going to say generate outputs. And where did it go? Here we go, generate outputs. Okay, and let's go back to Gerber files, configure. All right, and there's the outline. All right, so we'll see what it calls it. Good, and we're going to say generate. And it's going to put it in that same little place. Looks good to me. Close, and here it is here, everybody. And let's extract. No. Extract all, and I want to extract it right here. Okay, let's move this one out of the way and get the extracted files. There they are. So there's our Gerbers again. Okay, now you can see there's an outline. All right, so now what I'm going to do is get back to that Gerber viewer. All right, and now let's take top layer just for a sanity check real quick. Okay, that looks correct. Okay, now let's take this outline. And there it is, there's the outline. Okay, so that means that this zip file is good. All right, so that has the project in it. Okay, so now what we're going to go do is we're going to go here, and we are going to go to something like Osh Park, which will allow us just to drag something in. So what you do is you take your zip file with your Gerber files, and you just drag it in there. So I'm just going to drag it in here. And if it can process it, then it means that everything is probably okay. Okay, so look good, processing, warning, your project doesn't contain a bottom silk screen. We knew this, right? Okay, so this all looks good. Warning, non-critical, your project doesn't contain a bottom silk screen. That's fine. So let's scroll through. So that's what it's going to look like. All right, and it does this really nice render. It looks real, which is kind of cool. There's the top and the bottom, not much to it. Very simple. So that is it. So we've gone through everything. So the bottom line is that is our GPIO expander. So that's how you build a breakout board. So in reality, this probably, took 2 hours for me to kind of do it. I would probably spend another hour or two kind of going over it and cleaning it up and fixing it, re-verifying it. So the process takes, maybe 4 to 8 hours to do it like a simple chip on a breakout board. So, you could do one of these, you could do one a day, one a week, send them out, make a product, put it on Seed Studio. So, you could do that. Anyway, the project is called CCE GPIO Expander _ V01001, or if you just search for Andre Lamoth or Crash Course Electronics, you should be able to find this and you can fork it. I don't know if this is perfectly correct. We may have made a mistake, but I'm going to stop right here. And then if there is anything wrong, you can fix it and do whatever you want with it. So that is the end of this bonus lecture. And it's probably going to be 2 bonus lectures, like a part 1 and part 2, now that I'm doing this and thinking about it, because I haven't, of course, edited it because I'm talking to you, but I'm going to go edit it right now. So anyway, I hope you guys enjoyed that, and I know this stuff is tedious, but this is the real process. There's another guy that does PCB design. His name is Robert Fernecki. And he does really complex motherboards, and I mean, he spends hours and hours just trace after trace after trace, and I mean, you just got to really sit through it, and because you learn little details, and it's tough. And I know it's hard to keep here and keep watching the video and stay here and do it, but it's worth it in the end. This is how you learn. All right, everybody. So I will see you in the next bonus video. Bye.